Hello, everyone. My name is Anwer Al-Kaimakchi. I'm a PhD candidate at the FMU FSU College of Engineering. My advisor is Michel Rambo-Roddenberry, and my presentation today is about stainless steel strands for pretensioned concrete girders. This presentation is part of a project funded by the Florida Department of Transportation. Here is the outline of my presentation. I will give a brief background about stainless steel material, then talk about the mechanical characteristics and bond strength property of the stainless steel strands, talk about the girder fabrication, flexural test, and flexural design, and then I will finish with conclusions. So stainless steel material has a high corrosion resistance property, and it has been used in construction industry for many decades in a form of V-bars. Recently, around a decade ago, stainless steel material was produced in a form of 7 wires strands, and those strands are proposed as an alternative to carbon steel strands in extremely aggressive environments. The question is, why stainless steel strands? Because it's a corrosion resistant strands. If you use carbon steel strands, then those strands are susceptible to corrosion, and corrosion is one of the major challenges facing transportation industry. If your girder is in extremely aggressive environment, then you may lose some of the capacity due to corrosion of the strand. On the other hand, if you use stainless steel strands, then you will mitigate the corrosion problems, and then your structure will have a lower maintenance cost, and then the service life of the structure most likely will be increased. So stainless steel strand has completely different mechanical characteristics compared to carbon steel strands. Recently, a new ASTM was released, A1081, which specifies the minimum guaranteed mechanical properties of the stainless steel strands. The ultimate stress is 240 compared to 270. The ultimate strain is 1.4 compared to 3.5, which is significantly lower, and the elastic modulus is lower as well. If we investigate the stress-strain behavior of the strands, we can see that the stress-strain for the carbon steel is rounded once the elastic modulus is deviated, and then we can see that the stress keeps increasing up to failure. We don't have a plateau compared to the carbon steel strands. We can see that the ductility of the strand is significantly lower than the carbon steel strands. Therefore, if you want to use the design guidelines specified for carbon steel strands, you cannot, because they are not applicable because of the differences in the mechanical characteristics. So to determine the stress strain curve, we tested multiple 0.6-inch diameter stainless steel strands from 2 spools in tension following ASTM A1081, and then those are the stress strain curves. All the tested strands satisfied the ASTM A1114 requirements. Also, we tested the strands in bond strength following ASTM A1081 to quantify the bond strength of the 0.6-inch stainless steel strands with the surrounding concrete. This is the test setup, and then here is the force displacement diagram. We can see that the minimum strength at 1 point inch displacement was 15.8 kip, and then the average strength is 17.8 kip. This ASTM does not specify a minimum threshold, but we compared our result with the results for carbon steel strands in the literature, and then we saw that the stainless steel strand has a comparable bond strength compared to carbon steel strands. Girders fabrication, we fabricated 5 H2 Type 2 girders at Dual Stress Casting Yard in Leesburg, Florida. All 5 girders were casted in one bed. 2 of them had 11 stainless steel strands, and then 2 of them had 9 stainless steel strands, and then 1 of them had 7 stainless steel strands. So the only design variable was the pre-stressing reinforcement ratio in our study. Some photos from the fabrication. We used regular chucks, wedges to tension those strands, and then we installed 2 vibrating wires to measure the pre-stress losses in the stainless steel strands. We also measured the transfer length using internal and external fiber optic sensors, And then to validate the strain measurement from the fiber optic sensors, we also installed strain gauges. And then we, from those readings, we determined the transfer length. In conclusion, fabrication of girders pre-stretched with stainless steel strands did not require any different procedure or equipment compared to the fabrication of carbon steel strands. It was smooth, very easy, and then we didn't face any difficulties during fabrication. Flexural tests. Here's the test setup. We tested the girders in 4-point bending. This is one of the girders before being tested. We did the test at the FDOT Structures Research Center in Tallahassee, Florida. We installed multiple strain gauges in the constant moment region at the top fiber and also along the depth of the section. We had multiple deflection gauges along the length of the girder. And then we also installed slip gauges at the bottom of the stainless steel strands to monitor if we have any slippage of the strands during the flexural test. Load deflection results. Here's the load deflection, load mid-span deflection. We can see that the capacity increased up to failure, and then without a yield plateau. So the capacity kept increasing up to failure, and then the failure happened due to rupture of the strands. You can see here one of the girders after being tested. Failure occurred due to rupture of strands here, and then we can see that the concrete and the compression zone was still intact, which means that the strain in the compression zone or at the top fiber did not reach its ultimate capacity of 0.03. Here's like a picture where you can see all the strands broke. So even though the stainless steel strands have low ductility and the behavior of all girder was controlled by the low ductility of the strands, we can see that all girders exhibited significant reserve deflection and strength beyond the cracking load. So here's the cracking load, and then we can see that all girders exhibited significant deflection and capacity after cracking. Also, flexural cracking cracks are all girder exhibited many flexural cracks before failure, would serve as a sign that the girder is reaching its ultimate capacity. And then we can see here that the flexural cracks extended beyond the constant moment region, and then also they're kind of uniformly distributed. So even though all girders failed due to rupture of strands, they exhibited many flexural cracks, which was telling us that, okay, the member is reaching its ultimate capacity, and then it failed. Flexural design. So all the girders tested failed due to rupture of the strands, which means that the strain in the bottom layer of strands reached its ultimate capacity, while the concrete in the extreme compression fiber did not reach its ultimate strain of 0.03. Therefore, the stress block factors alpha 1 and beta 1 cannot be used, those specified in the ACI, because the values given in the ACI 318 are only for the strain when it's equal to 0.03. So here we have two unknowns, alpha and beta 1, and then if we want to calculate the neutral axis depth, then we cannot, because alpha and beta are unknown, and then we need to do iteration to determine those values. So we propose an iterative approach to determine the nominal capacity of the strands. It's very simple. You start with assuming the concrete top fiber strain, and then from the strain distribution, you will calculate the neutral axis, the first neutral axis depth. Then these are equations for beta and alpha, which were proposed by the NCHRP report 907. And then after calculating those beta and alpha, you will calculate the neutral axis depth using the equilibrium equation. And then you will keep iterate until your C1 minus C1 equals to 0. And from there, you can calculate the nominal moment resistance. This is where the values given in the ACI 31819 cannot be used because those beta 1 and alpha 1 are given only when the strain in the extreme compression fiber equals to 0.03, where those equations can be used for any strain in the compression fiber. We also developed an analytical model based on strain compatibility and force equilibrium. This is the load deflection. We can see that results obtained from our analytical model were in a very good agreement with the experimental results. So we use this analytical model to conduct parametric studies where we develop numerical equations that can be used by bridge designers. And also we use the parametric studies to develop design guidelines for the use of stainless steel strands in pretensioned concrete members. Prediction of experimental results. So as I mentioned before, we use two approaches. One of them, strain compatibility. Actually, this approach requires a lot of computation. And then the second approach was the iterative approach. It's a straightforward, requires simple iteration. And then here we can see that both approaches they predicted the experimental moment very well. The iteration approach was very simple compared to the strain compatibility approach. Conclusions. Stainless steel strands is a viable option for concrete members in extremely aggressive environment. They are available in two sizes, 0.52 inch and 0.62 inch. Recently, ASTM A1081 was released in April 2020, which specifies the minimum guaranteed mechanical properties for the stainless steel strands. Stainless steel strand has different mechanical properties compared to the carbon steel strands. And then in our studies, the stainless steel girders exhibited multiple flexural cracks before failure, even they failed due to rupture of the strands. This was a good indication that you can achieve a high deflection even when your member is failing due to rupture of the strands. And we propose a simple iterative approach to calculate the nominal moment resistance of the girders pre-stretched with stainless steel strands. Thank you so much.
Thank you, Anwer, for the interesting talk.